So in this session now we are going to see some of the theoretical concepts that I explained in the last session, right? How we can do in terms of coding. Okay, so here I'm not going to use it from scratch. Rather, I'm going to use some concept that was proposed by the original papers of LSTM, right? So I'm going to demo that code itself. Okay, so here what is there is that I have taken directly from my website. Okay, so there you can also see that. So it's an example of many to one classification, right? A sequence will be given and we need to classify to which class does it belong to. Okay, so if you can read it, the goal is to classify the sequences. Elements and targets are represented locally. Okay, so and okay, let me explain that with a example. So there would be sequences and we need to classify the actual class to them actually, or we need to predict to the class do they belong to. Okay, so let me show you one of the sequences, then I will explain what is the input, right? So let me show this. Okay, so here you see we are taking a sequence. You can think of this sequence, okay, that is, or I will take another sequence just to show you. I'll come to this point. What is this? So you see a sequence is there. Okay, so the input would be a sequence, and in that sequence the starting letter for begin will start from B, and the end letter will start end letter will be E, right? So capital letter B will be the start of the sequence and the capital letter E will be the end of the sequence. Then the sequence will consist of letters, small letter A, B, C, D, but in between what will happen, there would be the letters like this X and Y. Okay, so X and X you can see over there. Even you can get X and Y. Let's say if I change the sample number over here, I can get some, one second, I can get some other sample. Okay, so you see, this is generally like consisting of a first letter B and letter E, and then in between you have the letters A, B, C, D jumbled, right? That they are generated randomly. Then you can have two letters X and Y. Okay, only two letters, either X or Y. That means some position you can have a letter X or Y, right? So like in this case X and Y. Okay, only one. Now if the sequence of X, like in the let's say the ordering of X and Y, they follow this ordering, then we define the corresponding classes. Now if a X appears before X, then we will say that it belongs to class Q. If a X appears before Y, then it is class R. If a Y appears before X, then it is class S. And if a Y appears before Y, we can say that it's class U. So you see there are four classes depending upon the ordering of the X and Y, right? So that is how the data set is defined. So it's a very simple data set. Let us see how the models that we discussed is going to work. More specifically, two models, the simple RNN model and the LSTM based model. Okay, again in that they have defined, okay, different levels of difficulty. Okay, so difficult levels like easy level is there, then normal level is there, then moderate level is there, even moderate level is hard is there. So if I select, let's say, easy, right? So if I select easy and I generate a word, you will see that very small words will be generated. Okay, like of length 8, 1 2 3, I think 4, 1 2 3 4 5 6 7. Okay, so different very small letters plus very small length sequences will be generated, and then they can be classified. So if I make it, let's say, instead of easy I make it normal, and see what is the sequence that is generated, you will see that a little bit bigger sequence will be generated. We can make this also hard and see what is the sequence that is generated. So you see a harder sequence will be generated, but it follows the same rule, like starting from B and ending from E. In between you have the jumbled sequence of A, B, C, D, small A, B, C, D. But in between you can find out this letter X and Y, and depending upon the order of this X and Y, so you can find, you see there is an X over here and there is an X over here. So X means it's a class level Q. Right, so depending upon the order of this X and Y, actually it is defined whether it belongs to class Q or R or S or, right? So if X comes before X, then it is Q. X comes before Y, then it is R. Y comes before X, then it is S. Then Y comes before Y, it is U. So you will see there are four classes: Q, R, S, U. Now let us go to the network right, defining the model. So here we have used PyTorch. Okay, so I'm not going to discuss about how the installation and all those things. I hope you know how to install all the libraries that are required for deep learning and all. So here I have directly used the Torch library or PyTorch library to be specific, the Python library, sorry, Python wrappers for this PyTorch whole package, right? Or PyTorch programming language or whatever. So then we have defined a simple RNN model, right? In case of simple RNN, directly there is a function in PyTorch which is torch.nn.rnn. Okay, directly we can give the RNN, and there we can pass the input size as well as the hidden size. What would be the hidden size means how many outputs that you are going to expect in your each recurrent state. Right, so hidden size you can give, even non-linearity you can use any non-linear activation function like sigmoid or 10 hyperbolic or ReLU, as I told you in element network. So this is, you can think of like the element network, simple RNN model with which connects between input size and output size with a non-linearity of ReLU, right? Then there is a linear combination to find out the output. Okay, so this is for the last stage, which take the last hidden size output with the output size, whatever the output that you are going to expect, right? So in this case, you can think of like output size equal to 4. So I think you would have developed very simple neural networks models like multi-layer perceptron or convolutional networks. This is just the same. We are not doing something new, just that we are using a new function called as RNN that is already there in this torch library. Okay, and this linear is the direct, it is like fully connected network, fully connected connections from one layer to the other layer. So that is where this linear combination is used. Then the forward function, like we have already done, like you just pass the input, then again you pass the output of this, the hidden state or the recurrent state to the final output layer. Right? This is the simple RNN model. Okay. Then there is a simple LSTM model, okay, which is again directly in the PyTorch. There is a module called as LSTM. You can directly use that. So simple dot LSTM, sorry, self dot LSTM equal to torch dot nn dot LSTM. There again you need to give input size and hidden size. Again the linear will be again combination from hidden states. It will take the size of the hidden size and the output size. So whatever the number of or the length of the recurrent state, that will be the input over here, and the output would be the output size that you actually require for your prediction task. And it is same as like the forward function remains the same. Okay, then these are like this is not that much important in the context of what we were discussing. Then the training loop, like we were discussing for any of the neural network, I think you would have of course you would have done the programming for other like this convolutional neural network or multi-layer perceptron. Similar way, you need to run the training loop in iterations and see how the output is. Okay. So I'm not going to discuss about how the training loop is written. It is similar to what we were discussing, or what was being discussed throughout your FDP, right? How we do the training loop, how we call the uh, samples one by one to, or you, if you pass in batches, what would be the loss and all, and then you pass it through a optimizer to actually optimize through the gradient descent, stochastic gradient descent, or Adam optimizer, whatever, right? So this is generally the training loop that we generally write in case of neural network. So nothing new in that. So we are not going to discuss in details about that. Then again the testing loop. So in case of testing loop, generally you do not do any weight optimization. Just you see how the accuracy is and all by passing the testing data. So again, this is same as whatever was discussed previously for your neural networks. Right. So let me just run it. Okay. If I don't run, then it will not run. Training loop, then this is the testing loop. Okay, then putting it all together, like many libraries are there. So again, then there is this train and test function which will actually will be called to do the training and testing. Like it will do the training side by side, it will also pass the testing data to see how the output is, right? So that is why this train and test is written. So there the train data will be passed as well as the test data will be passed, and at every epoch the training accuracy and the testing accuracy will be shown. Okay, so that is what is written over here, again with the same concept of like iterations you have to pass the pages and all. Okay, now we'll come to the main concept. So these are like very general concepts of neural networks, like how you write your train loop, how you write your test loop, and how you call them and all. So nothing new to that. Maybe here and there some changes would be there, but with respect to RNN and LSTM, there are not many changes. So the same kind of training loop and testing loop can work for, let's say, if you are working for convolutional network, just by changing the training data and test data, it is going to work. Right? So we are not going anything specific with respect to the RNNs or LSTM. The most important thing to remember from the previous blocks is that how we define your RNN and LSTM. So if you see the RNN, you see it's a simple RNN with a combination from RNN to linear. Then you forward it, then a LSTM function which is taken from directly a LSTM module is there in dots.nn, and that is called with your input size and the hidden size. Then you again write a linear function which can actually give you the prediction, right? So that is taken from hidden to the output size. So these two things if you remember, then we can directly go how the data can be passed. So, okay, so let us run this simple RNN model, right, that we have detected for, let's say, EG samples. Okay, let us take some EG samples like I showed, right, very EG samples that were there. So let us run that, right? Okay, so we can run it. Let us see. So you see, we have taken 30 epochs. Okay, even we can take some, even you see, we can take 10 epochs and see how the output is. So cross entropy loss is used. So in 10 epochs, you can see it is reaching up to accuracy of 48.29. And if you see the loss versus accuracy curves, right? So this is the accuracy, this is the loss one. So in case of loss, we can say that it is very erratic within 10 epochs. We have run it for 10 epochs, so it is not converged yet. So let us increase the number of epochs to, let's say, 30 epochs and see how the results are. Right. So you see in 30 epochs, it is actually learning well, and it is able to converge, and it is able to reach the 100% accuracy for test. Okay. So even if you see the training plot, so epoch versus loss, it is decreasing steadily. At some points, the you can find out the peaks also, but at the end, it is converging well. Even the accuracy, I think by the end of 15, 16 or 18 epochs, it has already reached to the 100% accuracy. You can see it from here. So by the end of, like, I think 19th epoch, it has reached to the accuracy of 100%. But let us, instead of EG level, let us take some normal level and see what is happening. What is happening? Okay. So if I see normal and then run for 30 epochs, so you see it is reaching up to a accuracy of 27% only, and the training is very erratic. Right? Even with normal level, the simple RNN is not working that well. But if I take some, let's say, hard level and see what is happening after 30 epochs. Okay, so you see in this case, still it is still less accuracy because we are giving the hardest level. And if you check with the training loss and accuracy, you can see this is very erratic. It is not even reaching to, we can't figure out anything from these curves. Okay, so we can again find out by taking 100 epochs, right, and see whether it is able to learn this simple RNN by taking 100 epochs. Okay, so let us see. Still it is not able to learn. So the, you see the simple RNN, by taking a very long sequence, it is not able to learn anything, and it is very getting very difficult for it, right? So you can see the even the training curve. So even though we take 500 epochs, it is not going to learn. So this kind of simple RNNs are not working that well for, if you take like, let's say, a simple RNN, if you take for very complex data, it is not going to work. Right. So now let us move to LSTM and see how it works. Okay, now we are comparing between the RNNs and LSTMs, right? So if you take the LSTMs, let's say we are taking the EG level, right? So and we run it for just, let's say, this just for 10 epochs. Okay, so we can run it and see. See, with 10 epochs, the LSTM is able to reach 50%. Let us run for 20 epochs and see. See, it is reaching very fast. Okay, it is reaching very fast to the 100% accuracy with the 20 epochs itself, right? So you see, LSTM, as I told you, is a better neural network than if you compare with RNNs, right? Because this concept of a vanishing gradient and everything is being handled with the help of this forget gate, input gate, and output gate, and all, right? Now, if we make it, let's say, normal, okay. So with this normal, what can happen is that let us run this and see, right? So if you see this, it is with normal data with 20 epochs, it is reaching up to 52% accuracy, not more than that, right? But if we make it, let's say hard, not hard, if you make this 20 epochs, let's say 30 epochs, and see what is happening. So the accuracy is increasing. It is, you see, for some time it is what it was not able to actually learn properly, but after that, once it tries to learn from the data, right, it is able to see whether x is coming before x, or x is coming before y, or y is coming, like if it is able to learn that, then slowly and steadily it is actually converging, and it is able to give you a good accuracy. Now it is with 30 epochs. Of course, if you go for 100 epochs, you can actually get 100% accuracy in this case. It should get, I'm not sure. Yeah, of course, 99.5%. So it is, you see, it is steadily decreasing, the loss is converging, and also it is able to give you a good accuracy if you compare with the simple RNNs, right? Now, if I take, let's say, hard lines, which the simple RNNs were not able to learn properly. So here again, we have run it for 100 epochs. Let's see how the results are. Still, LSTM is not able to learn properly in this case. We have taken LSTM, right? Yeah. So LSTM is not able to learn. Let us run for, let's see. So still, the loss curve error accuracy, if you see, it is not able to learn properly. Let us run for more number of inputs, 300 inputs, and see what is happening. Let it learn for more time. Still, the accuracy is not reaching up to 100%. So LSTMs are not able to learn with this set of sequences that we have taken. Maybe we will change something to the neural network. Oh, the hidden size is very small. Like in the previous case, what is the hidden size that is taken? 4 only. So maybe we can increase the hidden size and see by taking, let's say, 16, and see what is happening. Okay, that means we are putting more number of layers to your hidden state, right? So previously only 4 hidden state outputs we were getting. So let us now put 16 hidden states and see how it is coming. Still, the hard levels are very difficult to learn even with LSTM, right? But let us see the previous case when in simple RNNs we use just 4 number of hidden neurons. So let us use more number of hidden neurons and see how it works. So still it is not able to learn with even with 300 epochs. But let us go to the previous case when we use the simple RNN, and we will take, let's say, the hidden space as okay. Let us just 1 second. Okay, we have taken the hard level over here. So the input size is, of course, always it is represented as 8. So here this hidden size, those who are confused, this hidden size is the size of the Q value that you have taken. Like how would you represent the each output in the recurrent state by a vector. So like I told you, let's say you are giving a sequence, then in that sequence, every word will be represented by a p-dimensional vector. Now, if you go to the theoretical part, right? So let me open these slides once again. So those who are confused, let me just show the slides again, then it will be much more clear. Okay. So if you see this diagram, so this x, these are the like sequence, like as I told you, each x will be represented by a vector, right? So like p-dimensional vector. So in the previous case, here each x was represented by a length of 8. So that's why you see this length 8 is coming. So input size. Okay. Then it will be then each hidden state, like in this hidden state, what would be the size of this hidden state output. Okay, so I in the theoretical, when I explained, I told that it will be represented by a q dimensional vector. So in this case, we have taken, let's say at the beginning we took it as 4, right? So 4, so we are seeing by representing as a 4, so what it is coming, right? So that we can change and see what is the output that is coming, right? Okay. Right. So even with you see, if you take the hard level, even the LSTMs are not able to learn, let alone the simple RNNs, they are not, anyway not able to learn properly, right? But if we change the hidden state in case of simple RNNs and see what it is, right? So this code is not something that I have generated. It is already there. So if you see if you see this website, so in this website already the sequence classification using recurrent neural networks. So already they have used the concept. You see original experiment from Hochreiter and Schrumberger, which was published in the 1997 in the original LSTM paper. So in the LSTM paper itself, they have used this data. So it is not something that is generated by me. It is directly available in the web. Okay, so I have used that only to do the experiments, right? So just that you have to do is you have to create your environment. So in this case, what I have done is that I have created my own virtual environment. In that virtual environment, I have installed all these PyTorch and other libraries like Matplotlib, TQDM for generating the graphs. I have used this Matplotlib, right? And for generating these bars and everything, I've used this TQDM. So different libraries are there. So for that also, you don't need to worry. Once you take this code, okay, so you can see this. I am sharing the screen. So once you take this code and run it, right, so automatically you are going to get many errors, and based on that you can install through, I think most of you are familiar with Python, right? So you know how to install the libraries and everything. So you can directly install those libraries, and once you get the libraries, once you install the libraries, automatically you can run this code, right? So there is not something that I need to save this code also directly. So whatever the experiments are there, I have just repeated over here, right? Yeah, and I'm going to explain like what is going to happen. Let's say if I take this as eg. Okay, so we are trying this simple RNN. What is the simple RNN? Yeah, so let us take this as moderate. There is a something called as moderate, and let us see what it is. So in case of moderate also, the simple RNNs are not able to learn. You see, even though I have taken a hidden state size of 16, and still it is getting a 24.29%, 24.29% accuracy. But if I am using a moderate over here, in case of LSTM, and this is the 16 hidden state side out 16. Let us see what it is happening. But it is for 300 epochs. Let us be more practical, because it is for the simple RNN. We have run it for 100 epochs. So let us run this this LSTM also for 100 epochs and see. But here we can see, right, by the end of this. Okay, let us change that to 100 epochs and see. Okay, so first let it finish this 300 epochs, then we will run it for 100 epochs and see how the output is. So let us run this. So you see, this moderate, although the hard levels were not able to be learned properly, but in case of moderate level, you can see the simple RNNs, even with 100 epochs, they are reaching 24.29% accuracy at the end of 100 epochs. But in case of LSTMs, they were able to reach 100% accuracy by the end of 100 epochs, right? So if I, let's say, so this is like comparing with the simple RNNs with LSTMs, and you can see that LSTMs work far better. But of course, when the level is hard, of course, we need to do some changes in the neural network. Okay, just by changing the number of epochs and the hidden size and all. Of course, when you are changing the hidden size, you are inherently changing the neural network. But we can make it more complex by using more number of LSTM layers. Even there is a concept called as bidirectional LSTMs. So like we have discussed about bidirectional RNNs, we can replace that RNN unit with LSTM, and we can actually do this bidirectional LSTM. Even we can run a concept called as stacked LSTM, stacked RNN. So whatever the concept that we discussed, right, in theory, we can actually do the same thing with LSTM also, not only with RNNs, because I discussed about the single directional RNN, bidirectional RNN, then stacked RNNs and everything, right? So all these concepts can be actually brought together in LSTM. Like we can do bidirectional LSTM, bidirectional LSTM and stacked LSTM and all those things, right? Okay, so let us so this is 16 with moderate, and we are using the simple RNN model. Then still it is not able to learn. So let us do it for 300 epochs and see what is it. So here you see RMS prop, which is again a version of Adam. Okay, so if you see the gradient descent, right? So in case of machine learning, many numerical solution methods exist, like this gradient descent or this Newton Raphson. But in case of deep learning, if you remember, we were using stochastic gradient descent because there are lots, the data set is very, very large. And if you go for empirical risk minimization to find out the loss, then it will take too much of time and that complexity would be very large, right? So in those cases, instead of using the gradient descent, we came to stochastic gradient descent. Then again, we saw that there are some variation to stochastic gradient descent, like we can use the Bayes gradient descent. Then on Bayes gradient descent, we can actually use the momentum based parameter, right? From momentum, we saw that we can actually come up with something called as Adam optimizer, right? And we can also use the RMS prop. So RMS prop is one of the optimizers that could be used. Okay, so you can try the same code with by using different optimizers also. Like we can use, let's say, Adam optimizer and see how it works. Let us see. Okay, so this is moderate level with simple RNN. Okay, simple RNN with 300 epochs. Okay, let us see whether it is able to learn properly or not. Okay, sometimes the optimizer plays a very important role. How you do the optimizers, right? So still, you see, moderate level is not going learning properly in case of simple RNNs. Okay, so that means in case of simple RNN, whatever the RNN that we have used, very simple model of RNN, it is not able to learn properly anything other than EG level, right? So EG levels are able to be predicted properly, but apart from that, not any other level we are able to do it properly. But in case of LSTM, although the hard levels are we are not able to classify properly, but other levels like this moderate and EG are able to be done. So let us see this. There is a Let us try hard for LSTM with the Adam optimizer, not RMS, because Adam nowadays is being used widely. Okay. So Adam, you see, when I'm writing this automatically, the other versions of so Adam W is also one of the variations of Adam, which is being wisely used. Let us see first with Adam optimizer and see how it works. Okay. So still, the hard levels are very difficult to learn, and it is not learning properly. Even the LSTM is not able to learn properly. Okay, so you see, by looking, you see, these the plots are very important. So whenever you are doing any task, right, you always plot it. So these loss plots and accuracy plots actually tell so many things about how your model is learning. So from there on, you can learn like whether overfitting is happening, whether underfitting is there. All these concepts can be easily be done with the help of this, can be easily found out with the help of this loss plots and accuracy plots, right? Let us try with something called as atom W and see how it is. Still, the hard labels are difficult to learn. Okay, even LSTM is not able to learn properly. Okay, so these are the combinations that we could try. Let us try for, let's say, by taking the hidden state size a little bit. So we are not making it more complex, this LSTM, by taking hidden state size. With the hope that it can go with the good accuracy. But still, it is not able to learn. Right? So these are the different combinations that are there. Okay, I have taken, although we have tried, I think, for 100 epochs and all we have tried. So if you like this, if we put verbose equal to true, it will actually show the epoch accuracy and all as it goes on. So here it is a easy level, so it is showing with accuracy. So all these things we have tried actually, so we don't need to, yeah. Even you can see the model evaluation by taking some data, right? So let us do that and see how it is performing on new data, right? Okay, so difficulty level we have passed. So you see Q 250 out of 2. So it is like 100% accuracy. So for Q, there are 250 samples, all are correct. So for all of them, it is coming correct. So that's why 100% accuracy it is coming. I don't know which model have it has used. So model, what is the model that is passed? Let us run the LSTM one. Okay, so let us run the LSTM one and see with, of course, with EG it is going to come 100%. Let us try with hard. So with the EG, you can see it is coming 100% accuracy, and that is not a surprise. But with hard, let us see what it is coming, and then we will see how the results are. Okay, so it is giving only 24.19 accuracy. Now let us see how the results are on some of the sample data. Yeah, you see, it is just like it is able to learn. You see what is happening over here in case of LSTM. It is 251 out of 251. That is means it is able to learn the Q out of like Q's classes very well. But for other classes, it is nothing learning nothing. Right? So it is biased towards Q classes. So like this X sequence, if it is there, then it is learning very fast. But for other sequences like X Y Y X and Y Y, it is learning nothing. Okay, so yeah, so you see these are all sequences where I think first few sequences where Q is there. Okay, so maybe some bringing some randomization like by changing the sample numbering, how they go into the neural network, all those things, like by bringing randomization actually we can actually improve this LSTM neural network. Okay, so we'll not go into details of that in the interest of time, right? So yeah, okay. So with this, I'll stop this session. Okay. If there are any doubts, you can ask. I will. So there is nothing to say for this code because this code I have directly taken from the LSTM paper itself, right? So this code is widely available. So those who are interested, they can see that code. But at the same time, if the organizers they request me, I can share this link. No issues with that. Yeah. Any questions? Okay, there is, sir, please maximize your screen. My screen was not visible. The organizer, is there anyone?
No, sir, it was visible.
Okay. So any latest trends for, there is one question like any latest trend for RNNs and LSTMs. So I would say that RNNs and LSTMs are now a thing of the past, right? So previously when the sequential data handling was being discussed, like during the 2000, you see this LSTM was proposed in 1997 only, although they were actually be used in the sequential data towards the 10 to 2015 or 2016. But still, with the advent of this all these transformers and everything, where sequential data can be handled more efficiently, now there are not much of a research that is going on in the direction of RNNs and LST, right? So if you want for latest trends in the direction of handling the sequential data, I would say to see these transformers, right? So they are better in handling the sequential data. Yes. Any other question, participants? So coding wise, my suggestion is that you need to first get hold of very basic concepts in writing the neural networks, right? So once you do that, you see there are many things that I discussed over here. If you see this code, like there are many concepts like how to generate the train function, how to write the train function, how to write the test function. If you see this, there is nothing to be discussed over here, because this is similar to everything. Even if you take the image data, even you take the text data, audio data, doesn't matter. So you need to get the data, you need to get the target, you need to get the training loader, you need to get the testing loader. At the end, you need to pass it through the neural network. So there is nothing much to be discussed in the concept of how the training goes or how the testing goes. Of course, there are many hyperparameters that we need to set, like what would be the learning rate, what would be the optimizer that we need to set, how many epochs that you're going to run, if there is any what do you say, regularization that you are going to use, if there is you are going to use like momentum parameter and all. So all these hyper parameters of course are there, but once you do some experiments on your own, automatically you will get hold of that. That is not a big deal. The biggest problem in neural networks or in general in case of machine learning, how to handle your data. Let's say you are talking about data, like what kind of pre-processing that you need to do, how you are going to use it in your neural network. So that is the first part, like handling the data. Then comes the biggest part, like writing the neural network. What kind of neural network is going to work for your data? You see, for different kind of data, different kind of neural networks can work. Okay, there is no foolproof method that if some method is work for some kind of data is going to work for your data also. That is not going to happen, right? So you need to see for your kind of data what kind of neural network is going to work. Like I gave you an intuition by I was explaining this bidirectional error, and is that there is some words that are known to us. So why not use a bidirectional error so that such that information can be incorporated, right? So with this intuition, you start and see what are the neural networks that exist that can work for your kind of application. Then it is going to be successful, right? So coding is a skill, I would say. You need to do practice always and then get the hands on it. Of course, there are many GPTs nowadays available which can give you directly the code once you write down your requirement. That is of course there, but my suggestion is that try the coding on your own first. Then if it is not happening, then you actually see the GPT and all. So at the end of coding, the first thing that you have to do is to learn the algorithm, right? The step by step process how you are going to solve your problem, right? So if that is clear to you, then automatically your problem solving skills, critical thinking skills is going to increase. Okay, so nowadays even I see many students, okay, we are all faculty members, I hope, because it's a FDP. So we see all the students without thinking, even if you give any question as an assignment, or whether in a theoretical assignment, whether it's a live assignment, they directly see search the internet, right? So that way they are losing their capability of problem solving and critical thinking. Okay, so as a faculty member, we also need to think in that direction. Okay, so before actually going to GPT, okay, or any other generative thing is there, first you try on your own, see how whether you are able to solve that problem or not. Then you see whether it is correct or not, right? By that time, you of course, if you do on your own, some kind of critical thinking is going to be actually developed, right? So that is what you should be the way to actually do the hands on. Yeah, any other questions? Okay, so if not, can we close this session?
Yes, sir.
Organization.
I
Yeah,
think there is no more questions.
yeah.
Mm.
We are also
So,
7:20, I think, was the time, right? We
yes,
have
sir.
reached to that time. Yeah,
So, thank you, Dr. Ramsar, for joining us in today's session.
yeah. Thank you,
So,
thank
you
you.
can leave now.
Yeah, thank you, the organizers for calling me for this talk. Yeah, it was a
You're
pleasure
welcome.
giving it up. Thank you.
And thank you to all the participants for joining in today's session. The quiz will not be held today. It may be conducted tomorrow or day after tomorrow. I will inform the timings in the WhatsApp group. So the participants also can leave. Thank you.